So the title of my talk is Squeezing Quantum Uncertainty by Entangling Atoms. And I thought I would start, since I have these terms quantum and entanglement in my title, by sort of giving a whirlwind introduction, so we're all on the same page, to just the general concept of quantum information. So all of you have a classical computer where information is stored in bits, right, which physically might be something like the orientation of some magnetic domains on your hard drive. One orientation could be a 0, the other one could be a 1. And actually, if you shrink this down to the level of a single particle, a single magnetic moment, or we call it a single spin, that actually gives rise to what we might call a qubit, a quantum bit. And here, similarly to the picture in the classical case, you could have a qubit that's, let's say, I think of as this vector pointing up, and that would be a 1. If it's pointing down, that would be a 0. But what's different about quantum information is I could also have a vector that's pointing sort of somewhere in between. And what that means in this picture is that when I measure the state, is it a 0 or is it a 1? There's some probabilistic aspect of this measurement. The outcome is going to be random. If this spin is tilted more up, it's more likely to be a 1. If it's more down, it's more likely to be a 0. But the state is somehow fundamentally undetermined until I do a measurement. And when I do the measurement, it's a little bit like tossing a coin. So that's sort of one of the kind of remarkable things about quantum mechanics. The laws of nature are probabilistic. But also, this isn't just any old coin toss. This is a very special type of a coin toss. So here's something that can happen in quantum mechanics that might surprise you. So in quantum mechanics, I could have a situation where Alice is tossing coins. She measures some random outcomes, heads, tails. And Alice, let's say, is in my lab at Stanford. Bob is in a lab here in New York. And Bob also tosses some coins. He sees some random outcomes. But when Alice and Bob compare notes, the outcomes are always correlated. Every time Alice gets heads, Bob gets tails, and vice versa. So in quantum mechanics, there can be these correlations within the randomness, which we call entanglement. And this phenomenon of this really tells us that there's information that Alice doesn't have and that Bob doesn't have, but that's somehow distributed across delocalized between them, in this case distributed across this long distance from California to New York. So that tells us there can be information that's not local, but that's stored in correlations. And that has a number of kind of profound implications for a range of different technologies that I think different lectures in this series might be telling you about. So the fact that you can have this sort of information that's delocalized across a long distance can have implications for secure communications across long distances. The fact that there's information not just in individual bits, but in the correlations between these quantum bits gives rise to the sort of exponential complexity of the description of a quantum system, where having even tens of quantum bits, one can have a system that's impossible to describe on the world's largest supercomputer. That has implications for computation and for perhaps leveraging this phenomenon of entanglement to enhance computations. And the third direction, which is the one I was asked to tell you about today, is the fact that the probabilistic nature of quantum mechanics inherently gives rise to quantum uncertainty. But entanglement can actually be a resource when we're faced with quantum uncertainty for maximizing the precision of measurements. Quantum uncertainty, you may have heard of the Heisenberg uncertainty principle, which tells you can't know sort of where a thing is and how fast it's moving, its position and its momentum at the same time to arbitrary precision. There are other versions of this uncertainty principle. There's one that relates measurements of energy and of time. It turns out to very precisely measure time, you need a system fundamentally with a large uncertainty in energy. And much of sort of modern research in this area of quantum measurement is learning how does one sort of manipulate uncertainty to our advantage? How do I engineer a system, for example, with a large uncertainty in energy so that I can more precisely measure time? And so, OK, if you'd like to sort of learn to manage this uncertainty, It turns out that actually managing uncertainty is something that one deals with in all walks of life. But in physics, when dealing with quantum uncertainty, physicists like to really sort of understand what are the microscopic origins of the uncertainty. And there's a beautiful sort of set of letters that was written back in the 1940s, going between Albert Einstein and Niels Bohr, where they were really grappling with this concept of quantum uncertainty. It sort of popped out of the equations, but sort of what's the physical mechanism behind it? And in these letters, Niels Bohr drew beautiful little diagrams, really kind of illustrating thought experiments of why it is, for example, that if you try to measure the position of this slit, you're fundamentally going to result in some uncertainty in its momentum. And you can understand that because in order to measure the position of the slit, I need to send some light through the slit. And that light, a photon could bounce off of the slit and give it a momentum kick. And so because a measurement of position will disturb the momentum, I can never know both perfectly simultaneously. So that was one successful diagram explaining this position-momentum uncertainty relation. And then Niels Bohr drew this diagram to explain the energy-time uncertainty relation. And I don't even want to know what's going on there. It looks complicated. The nice thing is that actually in our present day and age, right, fast forward to today, we don't need to just do Gedanken experiments. There are sort of real physical systems where quantum uncertainty poses a limitation. So those include gravitational wave detectors, where the precision of interferometrically measuring the distance between two arms of an interferometer is limited by quantum uncertainty in the light field. They include atomic clocks, and I'll zoom in a bit on that example of where the energy-time uncertainty relation comes in. Precise measurements of magnetic fields. They're sort of real-world devices where the precision is limited by quantum noise. So let me zoom in on this example of the atomic clock. So first of all, why do we use atoms as clocks as opposed to something like this pendulum here? Well, there are a couple of different reasons. One is an atom can be an oscillator with a very high what's called a quality factor. You get many, many, many oscillations before the oscillation damps out. And that's related to the fact that the frequency of the oscillation can be very fast, from even trillions of times per second. But also, the oscillation frequency is set by the fundamental properties of the atom, which is to say, once I choose which type of atom I'm working with, and for example, the definition of the second is in terms of an oscillation frequency in the cesium atom. A second is after the cesium atom has oscillated about 9 billion times. Once I choose which atom I'm working with, more or less any cesium atom that I pick in the world is going to oscillate at the same frequency. So actually, I posed this as a question. Is that true, that any cesium atom, be it in Boulder or Paris or Tokyo, oscillates at the same frequency? No. Oh, I see some people shaking their heads. Why not? OK, good. Yeah, so the height at which I put my clock can affect how fast it ticks. Great. Yeah. Any other reasons? Motion? Yeah. Yeah. I can have a Doppler shift. If my atom is moving, that could affect the oscillation frequency that I measure. And the Earth is moving. Good. Yeah. Mm-hmm. Mm-hmm. OK, yeah, so there are various things that could perturb the clock. And in fact, these actually can be interesting features, right? If I can make a very, very precise clock, I can actually use it to sense differences in gravitational potential. There are questions about whether the fundamental constants that determine the rate of the clock ticking are really constant. And if you can measure that frequency over long periods of time, you can ask, are fundamental constants of nature really constant, or are they maybe changing in time? And then there are sort of perhaps more boring things that might perturb your clock in ways that you don't want. If the atom is moving, that will affect, its velocity will affect the rate of ticking that we measure if the atom is interacting with some other atoms nearby. And so as a starting point, in order to make these types of measurements, one wants a gas of atoms that is dilute, so I don't have interactions perturbing it, and where the atoms are ideally at a standstill. And so it's out of sort of that goal of precisely measuring time and precisely doing spectroscopy on atoms has emerged sort of a rich field of research where the starting point is to take atoms and cool them down. There are tricks for cooling them down using laser light to temperatures of roughly a millionth of a degree above absolute zero. So this is a picture of a cloud of some millions or perhaps a billion atoms collecting at a temperature of around the microkelvin. And once one can do that, there's actually a whole host of kind of quantum science applications that this opens up. Here I've shown a picture of a few labs around the world that are actually taking individual atoms and trapping each one at the focus of a laser beam. And there's an effort to use each individual atom as a qubit and use these as the building blocks of a quantum computer. There's also a broader direction of saying, short of building a universal computer, can I use this well-controlled quantum system to perhaps solve as sort of a special purpose computer for solving certain problems that are hard because they're inherently quantum mechanical, like asking how the entanglement among electrons gives rise to the behavior of, to the properties of materials. So one can build simple model systems and ask what collective behavior emerges. Or there's this direction of asking, how precise can we make a clock? And particularly, can we start to improve the precision once we get even to the regime where quantum uncertainty is what limits us? So I'm going to say more about how one can improve the precision of clocks when limited by quantum uncertainty, and then I'll veer off a little bit into some other applications that this toolbox opens up. So it's worth pointing out that even before I get to sort of manipulating quantum uncertainty, state-of-the-art clocks are just extraordinarily precise. So it turns out if you'd started one of these atomic clocks when the universe began and sort of let it tick, it would be off by less than a second today. And the basic task that you need to do in order to measure time this precisely is really actually just to measure the energy difference between two atomic states, which are related by Planck's constant to the frequency difference. That's this oscillation frequency that we talked about before. And that basic task, if you can do it well, if you're working with, let's say, a cesium atom, in terms of which the second is defined, you have a clock. But that basic task of atomic spectroscopy also lets you do things like precisely measure magnetic fields if the two states whose energy difference I'm measuring are sensitive to the strength of a magnetic field. Or could let you measure gravitational potentials if the two states are different paths of atoms through space, at different heights through space. So this is a very powerful general tool, this sort of tool of precisely measuring the energy difference between two states of an atom. And no matter which of these precise applications we have in mind, we can visualize the system, these two different atomic levels, as two different orientations of a spin in a magnetic field aligned with or opposite the field. And then if we'd like to do what we'd like to do is measure the rate at which these spins precess, which if it's really a magnetometer, that directly tells me the magnetic field. But more generally, even if this is something like a clock, it gives me this frequency, which is related, which is, for example, the frequency in terms of which time is defined. OK, so the picture that we have in mind is we can sort of represent, if I have many atoms, I can represent that by some vector on a sphere. That's the sum of the orientations of these individual spins. And what we do is we start by preparing each of these two-state systems in the superposition of the two energy states, which we said is represented by some vector pointing kind of in the xy plane here. And quantum mechanics tells us that that vector is going to precess at a rate that's given by the energy difference between the two states. And at the end of the day, in order to see if I want to measure the frequency of the precession, I can rotate this vector that has precessed to convert the acquired phase into some difference in populations between the spin up and the spin down state. And so I should just measure the difference in the number of spins pointing up and the number of spins pointing down. And now this picture is missing one thing, which is that when I do this measurement, there's going to be some quantum uncertainty associated with which way the spins point. And you can really, this sounds sort of vague. I replaced my vector by a fuzzy blob saying there's some quantum uncertainty. But you can really understand this physically as the fact that I have, n atoms. and each one gets projected into pointing either up or down. When I do the measurement, it has to decide to be in one of those states. And this is sort of that coin toss noise. If I toss n coins, there'll be some fluctuations order root n in how many I measure in the two states. And that gives rise, when I that means I have some fluctuation square root of n in the number I measure up versus down. In terms of my angular resolution, I should divide by the radius of the sphere, and I'll get an angular resolution that scales as 1 over the square root of the number of particles. And this is called the standard quantum limit. And now, I told you this arises from something like a coin toss, the sort of statistical fluctuations in a coin toss. And so now I can ask you, is this a fundamental limit, or can we do better? Checking whether you're all following.
I assume we could do better by the title of the talk.
Good. OK. So, right. Yeah, it sounds kind of, the name makes it sound like maybe it's fundamental, but it's not quite fundamental because this came about from the statistics of sort of uncorrelated events, right? But quantum mechanics tells us we can have entanglement. We can have these weird correlations between one coin landing heads and the other coin landing tails. And so if we can entangle the atoms, maybe we can do better. And there's a particular class of entangled state called a squeezed state, where one has some correlations between the spins that sort of conspire to reduce the fluctuations in this final measurement, so that if one coin lands heads, another one is more likely to land tails. So what I need is to generate some correlations between the atoms of a very particular form. And actually, it's about 30 years ago that the idea of doing this was first proposed in this sort of landmark paper by Kitagawa and Ueda. I remember actually reading this as a graduate student, and there's this line that said, realistic physical schemes are yet to be found for doing this, but they had a nice idea in principle on paper for how one could generate the right type of entanglement that squeezes the quantum noise. And the basic idea was to have a system where I have this thing I call SZ, which is essentially the population difference between the number of spins that are up and the number that are down. And they wanted a system where the energy scales as that population difference squared. So one way to think about this is if I just have spins in a magnetic field, the energy will be proportional to the number of spins aligned versus anti-aligned with the field. So having an energy that's proportional to that population difference squared actually requires some interactions between the spins. And in particular, I could write this down by saying essentially the energy for each pair of spins, I should look whether they're aligned or anti-aligned. And so the energy essentially being proportional to the square of the population difference means there's interactions between all different pairs of spins. What this gives rise to is a scenario where each spin precesses at a rate that depends how many other spins are up. If there are more spins up in total, the precession is faster. If there are more down in total, the precession is slower. And so this blob of uncertainty gets kind of twisted into something that's narrower in one direction. But the reason that this is hard is that sort of in nature, we don't usually find systems where sort of every particle interacts equally with every other, irrespective of how far apart they are. Most interactions we find in nature sort of decay with distance. So this is a sort of exotic form of interaction. And one way that we can make it actually in the lab is by having a situation where atoms sort of talk to each other with the aid of photons, because photons can easily convey information across long distances. And so we can build a system where we essentially trap these laser-cooled atoms between two mirrors, and light can bounce back and forth between the two mirrors and sort of convey information between arbitrary pairs of atoms, allowing them to interact. And so this has the feature that the interactions are non-local, which is great for generating non-local correlations and entanglement. And they can also be switched on and off. So the interactions are only there when the light is on. That's good for precision measurements because we said we don't want interactions between the atoms, for example, perturbing our clock. OK, and so in that setting, it's been possible to make these states with squeezed quantum fluctuations. And I've shown here kind of a plot of, by now, kind of a number of different experiments that have been able to demonstrate precision beyond this standard quantum limit, namely, so precision enhanced by entanglement. So the red line here is the fundamental limit of if you have entanglement, the best precision you can get. Up is higher precision on this plot. Horizontal is just the number of particles. So if I have more particles, I get better statistics. So that's good as a starting point. And then, so the direction of sort of increasing absolute precision is sort of the direction of lighter and lighter yellow lines here. And by now, there are a few different physical systems that have realized this type of squeezing and precision beyond the standard quantum limit. But the record is actually held in these types of systems where atoms talk to each other with the aid of photons, which are shown in green, these photon-mediated interactions in cavities. And in those systems, it's been possible to demonstrate, this is back in 2010, was an experiment we did really kind of taking this type of squeeze state generated by photon-mediated interactions among atoms, applying it in an atomic clock to improve essentially by a factor of 3 the time that it took the clock to reach a fixed precision. So that was back in 2010, and there's been lots of work building on this, both improving how far beyond the standard quantum limit the clock operates, up to a factor of 10 a number of years ago. And more recently, also, though, taking these tools, which we demonstrated sort of as a proof of principle, and starting to apply them to those really best clocks that are, I mentioned earlier, that sort of wouldn't be off by more than a second if you'd started them when the universe began. And so these are experiments from just the past couple of years, taking this idea of squeezing quantum uncertainty and applying it to getting closer and closer to improving the state-of-the-art clocks by entanglement. So there's a number of different directions you could envision applying this. Here are some examples of experiments that don't yet use entanglement, but that might benefit from it. This is some recent work in the Kolkowitz group in Wisconsin, where they actually have six different atomic clocks that are sort of separated by a few millimeters each in height, and they're doing extraordinarily precise measurements of the difference in rates at which these clocks tick, which one can start to use to really test questions about fundamental physics, test relativity, ultimately perhaps in regimes where quantum mechanics is also playing a role. One can use this to measure the gravitational potential of the Earth. I mentioned the same techniques are applicable to precisely measuring magnetic fields. Here's an experiment where sort of a cloud of cold atoms is scanning over the surface of a material, probing the magnetic structure of the material in regimes that aren't possible by other methods of microscopy. And one thing I want to emphasize about some of these applications is once one starts to build a sensor, be it using a clock as a sensor or sensing magnetic fields, there's a number of sort of figures of merit that you care about beyond just absolute precision. So what is the spatial resolution of the sensor? What is the bandwidth of the sensor? How large is its dynamic range? And for many of those applications, you would actually like to have more than just a single big entangled state. And so one direction that we've been interested in pushing in is sort of expanding the complexity of the entangled states that one can generate, either making arrays of multiple entangled states that can give you spatial resolution in sensing, or actually really starting to program actually the graph of entanglement between multiple ensembles of atoms. And so just to give a flavor of sort of why you might want to do that in a quantum sensing context, if I do just care about measuring one quantity, time, a global magnetic field, then what I want is just a single large entangled state where the quantum fluctuations are squeezed. If I want to measure a magnetic field gradient, then maybe I want to sort of prepare a single large entangled state, but orient my spins so that I have differential sensitivity to the field in one place or the field in another, and that requires combining these global interactions with some local control. If I want really maximal spatial resolution, maybe I want many independent squeeze states. But more generally, some of these same techniques for sort of engineering entanglement, if one has sufficient programmability of the structure of correlations in the system, can also open other directions in being resources for quantum computation, or being resources for more complex measurements where I want to measure not just a field in a particular direction, but the full sort of vector components of a field in 3 dimensions. Broadly speaking, we'd love to have a system where we can kind of use all the control that we have over light to actually program something about the structure of entanglement between our atoms. And what the sort of setting where we do this is we have, similar to what I described before, 2 mirrors that let light bounce it back and forth and convey information between these cold atoms. Between those 2 mirrors, we have an array of clouds of atoms, which in our case, there's sort of, you can picture about 1,000 atoms in each site of this array. Earlier I showed pictures of individual atoms. One could potentially also do that in the future, but right now we actually benefit from having some collective enhancement of the strength of the atoms interacting with the light field by having many atoms per site, and that's also advantageous for precision measurement applications. And what we can do is essentially we can have any atom talk to any other by sending light into the system, right? So by sending light into the system, I can have this sort of all-to-all connectivity that any atom can talk to any other. But we also have the ability to kind of locally manipulate the spins, either by magnetic fields or by optical fields to locally control each site of this array. And it turns out that those two tools we're finding are very versatile for sort of controlling the structure of entanglement in the system. OK, so to tell you a little bit more about how that works, I'm going to zoom in a little bit more to the details of the atoms we work with. So it turns out I talked about an atom as something that maybe has two energy states that I called spin up and spin down. But in the experiments, in our current experiments, we actually work with atoms that have three energy states that I call -1, 0, and 1, three different magnetic states. And essentially, the form of interaction that we can generate in this system is when we send light between these two mirrors, you can have a photon. We can, so for example, start with both atoms in the 0 state, send in some light, and a photon that bounces between them can essentially flip one of the atoms from 0 to the -1 state and bounce off the other atom and flip it from 0 to +1. So this gives us a mechanism for atoms in a way that, by light scattering between them, to form sort of correlated pairs of atoms in the +1 and the -1 state. Why do I say correlated pairs? There's nothing in this system that should dictate whether the left or the right atom is in the plus or the minus state. And so in general, you would expect this might be a mechanism for generating entanglement, where I have, again, this sort of correlation between if this one is heads, that one is tails, and vice versa. And to start to see that might be happening in the system, we can do an experiment where, again, we start with all the atoms. Yeah, question?
Why does that photon change the spin of one atom in one direction and the other one in the opposite direction?
OK, so one way you could think of this is if I just had two energy states. The simplest picture would be an atom in the excited state can emit a photon and decay into the ground state. And that photon can be absorbed by another atom, which then gets excited. And so this would give a way of having a process where essentially you flip a spin down. So by sort of changing +1, in the simplest case, this allows me to have some sort of spin exchange interaction. In the slightly fancier system with 3 levels, it allows me to sort of have an atom in the 0 state transition to the -1 state by converting energy into a photon. That photon gets absorbed by another atom in the 0 state, which turns into +1. So it's sort of that energy, the photon sort of transfers the energy between the two atoms. Does that make sense?
Yeah.
Yeah, great. Thanks for the question. I like to know that people are listening. So good. So I sort of gave a cartoon picture for 2 atoms. We work with many atoms. And so what happens in the system of many atoms is when I turn on the light that should generate these interactions, we can sort of, here's an illustration of 30 repetitions of the same experiment where we turn on the light. And after turning on the light, we ask how many atoms are still in the 0 state, how many atoms are in +1, and how many are in -1. And we look at this site by site in the array. So within each column, which represents a particular internal state, each grid point represents a particular site of the array. And so what you'll see is there's some fluctuations in how many atoms are in the 0 state versus + and -1. That's some of the randomness inherent in this quantum system. But you'll see correlations that if I have more atoms in -1, I also have more atoms in +1. So there's these sort of correlations within the randomness that seem suggestive of entanglement. It's not yet a proof of entanglement. I'll come back to that later. But that looks like sort of the right thing is happening in this system. So far, though, the correlations kind of extend across the entire array, right? There's no sense of spatial locality. Position doesn't matter. And that's because the light lets any atom talk to any other, irrespective of where it is within this resonator. So I said we wanted to start to sort of program the graph of interactions in the system. And there's a couple of tricks we have for doing that. But the first thing we need to do is actually make the position of the atom matter, right? And one way that we can do that is actually applying a magnetic field gradient across the system, so that the energy splitting between these three magnetic states, -1, 0, and 1, actually depends on position in the resonator, depends on the position in the array. And so it turns out if I do that, if I just apply a magnetic field gradient and I do the same experiment where I turn on this light that should generate this pair creation process, what I'll see is that rather than having correlations that extend across the entire system, I have correlations just within individual sites. So I've illustrated that here by saying if I plot the strength of correlation between the number of atoms in the +1 state on site I and the -1 state on site J, I have strong correlations here on the diagonal. So I have local interactions, but I've turned off the sort of non-local part of the interaction. OK, so that's one element of control. But what I'd like to do is actually controllably introduce interactions sort of between sites that I get to choose. And it turns out we can do that. So this is the local interaction. If I want to start to turn on some long-range interaction again, I can controllably do that by sending in two different frequencies of light. So now I have the possibility that one atom absorbs a photon of a particular energy. That photon gets scattered to another atom. The other atom emits a photon of a different energy, and that can bridge the cost of creating a +1 atom here and a -1 atom over there. So just by controlling the frequencies of light that we send in, we can control the distances at which interactions are on in this array. And it turns out that it's very easy to sort of modulate the light field and send in any set of frequencies we would like. And by doing that, we can actually build up very sort of a rich array of different sort of structures of interactions. And so what I've shown here is just sort of a gallery of some of the different sort of graphs of interactions between these atoms that we can build up in the lab, where essentially by controlling sort of some modulation of the intensity of the light, which dictates sort of which frequencies are present, we can control at which distances these atoms are allowed to interact. So even though physically they're in a one-dimensional line, I can connect them as though it were a ring. If I modulate the laser in the right way, I can also connect them as though it were a Mobius strip or a cylinder. And all of these pictures are sort of directly reconstructed from experimental data. So this is some reconstruction where if sites are close together, it means that there are strong correlations that we measure between the sites. And the bonds that I've drawn indicate the sign of the correlation. If it's red, it means spins on the two sites are aligned in the same direction. If it's blue, it means that we're finding the spins to be anti-aligned. These are a nice verification that we can program in a particular graph of interactions and measure the corresponding correlations in the physical system. OK, so what can we do with that? There are a few different directions that we're sort of excited about taking this control. So one is by having sort of this more programmability of entanglement that opens up the possibility of going both to richer quantum sensing tasks, but also making potentially resources for computation. Another direction is that actually there's a range of computational problems that can be mapped to the problem of minimizing the energy of a set of interacting spins. So a number of kind of real-world optimization problems you can map to this thing of energy minimization in a system of interacting spins. And if you can actually build that specified graph of interactions, you can ask the question, can the quantum dynamics help me to solve that optimization problem? And that's an open question, actually, whether sort of to what extent quantum mechanics can help with this class of problems. But we'd love to be able to explore that. And we can also potentially use this as a set of tools for this direction of simulation, and I'll come to that in a moment. But let me just briefly sort of give an illustration of sort of why we think this system is interesting from the standpoint of optimization. So it turns out that in this our system of spin 1 atoms, there's sort of a wrinkle I didn't tell you about before, which is that when we create these +1, -1 pairs, the energy of a +1 and a -1 atom in and of itself is a little bit higher than the energy of 2 0 atoms. So there's an energy cost to creating these pairs if I just look at the internal state energy. But it turns out that actually the system can lower its interaction energy by virtue of the fact that the energy in the internal states is going up. And we actually sort of, and so you can ask, let's say I build some graph of interactions where every spin wants to anti-align with every other spin on some triangular lattice like this. this is something that is kind of a simple example of what we might call frustration. The neighbors would like to point opposite to each other, but of course they can't all point perfectly opposite to each other. The best they can do in this case is to sort of orient themselves at 120-degree angles. And when we actually measure the correlations between the spins in our system, we see that that's exactly what they do. And so it's sort of an indication that this system is naturally finding low energy states of this interacting spin system. And one question is kind of how well does it do it? Does entanglement in the system help? And we would love to explore particularly to what extent this system solves these types of optimization problems well in the case where the problem is actually a hard one. So here I looked at this and I told you how the spins should align. But it turns out if I have a general non-local graph, these can start to be hard computational problems. And we would love to explore to what extent the quantum dynamics in our system can help to solve them. OK, so just to give another sort of detour into what else can you do with this toolbox. I mentioned earlier that having this sort of well-controlled quantum system could be a tool for simulating some problems from other areas of physics. I gave the example of electronic materials, but here's a sort of very different area that we've been thinking about is can we use these programmable model systems to explore some questions from the field of quantum gravity. So that might sound kind of like far removed from what I've been talking about so far. So let me kind of introduce this on a philosophical note. And so I'm going to appeal to a philosopher I like because he's the father of the atom. This is Democritus, who I found this wonderful quote where he says, sweet is by convention, bitter is by convention, hot and cold, color is by convention. And he says, in truth, there are but atoms and the void. OK, what does he mean by that? So to put this in more modern language, one way to say this is Democritus really was putting forward this notion that the macroscopic behaviors, taste, temperature, color that we observe are really sort of emergent phenomena where the microscopic building blocks are sort of configurations of individual atoms. But there's some new macroscopic behavior that emerges. So these days, that's sort of well understood for things like temperature and color. And as I said before, we can even look at individual atoms in the lab. So he says, in truth, there are but atoms and the void. And one thing that's still more of an open question has to do with what the properties are actually of the void. So here's sort of a depiction of curved space. And you can ask, is space-time really smooth, or does it also have some underlying more microscopic description like these atoms that were a revolutionary concept in Democritus's time? So what might that microscopic description be? Well, here's one. This is a drawing by M.C. Escher in which it's actually an illustration of a hyperbolic space. The way to understand this is that all of the fish you should think of as being the same size. But there's sort of exponentially more fish around the diameter than across the circumference. And so that actually tells us that the space has to have negative curvature. OK, so the building blocks are these discrete constituents, which in the Escher drawing are fish. Physicists don't think the discrete constituents of space-time are fish. But what you might imagine is that curved space and gravity emerge actually from somehow from quantum mechanics. So imagine that each of these dots here is a qubit. And the lines represent something about the structure of entanglement between the qubits. And in this particular example, the lines form some sort of a tree graph whose the number of points here is actually exponentially larger than the depth of the tree. And so this is kind of a discretized version of a hyperbolic space. And perhaps the question is, are there actually situations where having a certain structure of entanglement among quantum degrees of freedom gives rise to some kind of effective description in terms of curved space in this case, one additional dimension, that's the radial dimension here. So this idea that gravity might emerge from quantum entanglement is one that is a subject of sort of intense theoretical inquiry that so far has been sort of hard to test in the lab. if you want to test it, one approach is actually precision measurements, build very precise measurements of gravity in a regime where quantum mechanics plays a role. And that's one place where, as I indicated earlier, sort of quantum engineering can help. But another sort of complementary approach is to ask, can we start from microscopics, build an interacting quantum system, probe the structure of entanglement, and see whether there are cases where the structure of entanglement is best represented by some sort of a geometric picture in terms of curved space. Okay, so I wouldn't have known sort of how to go about doing this as a naive experimentalist, but I was very fortunate to collaborate with Steve Gubser, a brilliant theoretical physicist at Princeton, who was also actually a Simons investigator. And in collaboration with Steve, we actually had an idea for sort of what might be a microscopic model that one could build in the lab that would give rise to this sense of sort of emergent geometry and some emergent curved space as the best description of the entanglement in the system. So it's a sort of exotic model when you write it down on paper. It involves sites with interactions only at distances that are powers of 2. There's some tuning parameter that says, do the interactions shrink or grow as a function of distance? These are things that you sort of won't find in a material that you pick up in nature, but that we can engineer in the lab. And it turns out when we engineer that graph of interactions, we can sort of draw a picture like I did before, where I program in some structure of interactions, and I measure correlations in the system. And I'm going to sort of plot the sites. They're numbered here according to the physical position in the lab, but I'm going to plot them near each other if the correlations between those sites are strong. Now, OK, and I'll do it in these sort of 2 different regimes where interactions are either strong between nearest neighbors or strong sort of at large power of 2 distances. OK, so that gives us some sort of effective visualization of the strength of correlations, but we'll go one step further and ask sort of, let's draw bonds between the sites that are most strongly correlated. And if we treat each of those sort of pairs of sites that are bonded together as a new larger site and repeat this process, it turns out that this process of sort of finding the most strongly correlated degrees of freedom, grouping them together, and repeating and coarse graining gives rise to actually precisely this sort of a tree that is a description, a sort of discretized version of a hyperbolic space. And the interesting thing is this tree, right, these bonds aren't really physical. These vertices inside the tree aren't actually sites in my lab, but there's this description that just emerges, the sort of this discretized version of a hyperbolic space emerges as a natural description of the correlations in the quantum system. So this is, to me as an experimentalist, this helped me sort of appreciate this notion of what it might mean for curved space and perhaps even gravity to emerge from quantum mechanics. Now, the conjecture is that gravity might really emerge from entanglement. So far, I haven't shown you entanglement. I've shown you some measurement of correlations in this system. And we'd love to actually be able to say something about the structure of entanglement. And so, to go from saying we measure some correlations to we know that there's entanglement, there's a few different ways you can do that. So in the simple case, if I go back to not this fancy graph of interactions that I programmed in, but just every atom talks to every other, one way to prove entanglement is looking at quantum fluctuation. So taking ideas from this area of quantum measurement that I mentioned before and saying, if I can do a measurement better than the standard quantum limit, that's one way to prove that there's entanglement in my system. And so it turns out in the simplest example, when we turn on this light that generates these correlated atom pairs in our system, one can actually look at quantum fluctuations in different observables. This is something like that spin sphere I showed before. The axes are a bit different. That's details of having 3 internal states instead of 2. But roughly speaking, we can measure quantum fluctuations as a function of the angle of my measurement and see that if I sort of look along this narrow axis, I see some fluctuations that are squeezed below the standard quantum limit, and that tells me there's entanglement in the system. But it doesn't yet tell me anything about the spatial structure of entanglement. And so if I want to say something about the spatial structure of entanglement, then we need to ask a slightly more refined question. So one way that I can say something about the spatial structure of entanglement, let's say I have 2 halves of the system, the left half and the right half. I'll call them A and B, and I want to know whether there's entanglement between them. One way I can do it is by asking, can measurements on system B allow me to predict the outcome of measurements on system A to better than that standard quantum limit, which is to say, imagine I have a state where, or let's just say this, the Heisenberg uncertainty principle tells me that there's some fundamental limit to how well I can know both x and p, let's call them two observables. In our system, it's not position and momentum, but I'll use this notation. There's some fundamental limit to how well I can know both of these, which tells me that inherently, in any quantum state, those can't both be perfectly well defined. But what quantum mechanics allows is correlations in both these two incompatible observables, in both position and momentum at the same time. So in principle, it's possible to have a system where, for example, whenever x is positive in system A, it's negative in system B, and vice versa, or whenever the momentum in system B precisely tracks the momentum in position A. And so if I can make that type of a system, then I could have this sort of weird scenario where even though both position and momentum are fundamentally unknowable simultaneously in this subsystem, if I measure this one, I can determine either the position or the momentum exactly. And so that hopefully is a bit counterintuitive, right? It tells us there's again, these sort of correlations in the randomness. I can prove that there's entanglement if I can measure those in two incompatible observables. So another way to say that is I can't know the position or the momentum of system A alone simultaneously, but I can know the sum of the positions and the difference of the momenta simultaneously if the system is in an entangled state. And so in order to actually sort of probe entanglement between the two subsystems, what I would like to be able to see is that if I measure the sum of variables in the two systems, I'm going to call that x plus. The sort of fluctuations in the sum are squeezed in position. Or if I look at the difference between the two systems, those fluctuations are squeezed in momentum. So we can make the analogous state in our spin degrees of freedom and directly actually look at the product of uncertainties in the sum of the x's and the differences of p's. And if that product is small enough, we can prove entanglement. And that's something that we can do. In this example, we have 4 clouds of atoms, and we can prove that the left 2 and the right 2 are entangled with each other. And it turns out that sort of the ingredient for actually making this state where we maximize entanglement between the two subsystems is there's actually sort of a very elegant scheme for generalizing that to making any graph of entanglement that I kind of can specify by saying I have certain bonds and I want strong entanglement between the subsystems on the bonds that I draw in. So for those of you who like sort of linear algebra, if I give you a graph, I can sort of represent that as some matrix where I have a 1 in an element where there's a bond. And if I diagonalize that matrix, it will give me a prescription for exactly how I make the state specified by that graph. So I'll get some set of eigenvectors, which in this simple case where I have the left and right and I want them strongly entangled, those eigenvectors are sort of the symmetric and the anti-symmetric modes of the system. If these were oscillators, it would be sort of the mode where they're oscillating together and the mode where they're oscillating apart. And this essentially, so that tells me kind of which collective observables I should squeeze, and the eigenvalues tell me in which orientation they should be squeezed. And I can then make that state by essentially applying a global squeezing operation, which is these global cavity-mediated interactions. That would, for example, squeeze the symmetric mode of the system. I can then flip some spins locally that converts this sort of totally symmetric squeezing to squeezing in the anti-symmetric mode. I do that by flipping sort of the right half of the spins. I can do some rotation to orient the squeezed quadrature in the way that I want. And then I can do a second squeezing operation, which squeezes, if I first squeeze the symmetric mode, this will now squeeze the anti-symmetric mode. So this is kind of a general prescription, though, that lets me build up also more complex graphs of entanglement. And so, for example, we can, if I want to make a square structure of entanglement, it's just a sequence of kind of 4 squeezing operations mediated by these all-to-all interactions, interspersed with local control of the spin orientations with a laser that addresses the individual ensembles. And so in this manner, we've been able to not only kind of build up complex graphs of interactions, but also start to really provably generate entanglement of a specified graph in the system. And I said at the outset, this sort of entanglement is the key resource for a number of different quantum technologies. We can see signatures of entanglement in the squeezing of quantum correlations, which then also has applications in quantum metrology. But more broadly, sort of entanglement implies to us that information is non-local. And so to efficiently generate it, we like having access to these non-local interactions that are mediated by light. And I've shown you that the combination of those global interactions plus local control gives us sort of a really versatile toolbox for engineering entangled states in these systems of cold atoms. And we're excited about taking this in these several directions of sort of advanced protocols in quantum-enhanced sensing and metrology, expanding what we can do in terms of simulations. I touched on simulations of quantum gravity, but there are potentially also broader spheres of application in simulation. Actually asking, can we use this control of the interactions to engineer systems where minimizing the energy actually solves a computational problem? So with that, I just want to thank sort of the team of people who make these experiments go and offer to take any questions.
All right, thank you very much for that talk. So yeah, first here, and when you ask a question, there's a button on your seat or in front of you. Please press that so people can hear.
Yeah. Thank you very much for the very interesting talk. I just want to go back to the experimental setup.
Yeah.
So typically when we have entangled pairs, they're very fragile unless it's like guaranteed by, a very strong interaction. Mm-hmm. So at the outset, why do we expect in this shower of photons, these like pockets of cold atoms remain entangled?
Yeah, so there are a couple of aspects to that. So one is, you said unless the interactions are very strong. And you may be thinking of something where we're maybe asking about, I guess, a steady state or ground state of the system in the presence of interactions. What we do is a little bit different. We sort of controllably turn on interactions for a fixed period of time while the light is on, and then we turn off the light and we have a non-interacting system. At the same time, the question, and it's an important one, is sort of how do you make the interactions that the light generates coherent, right? You might worry that I send in light and the light leaves and the light carries away some information about the system. And so how does this fragile entangled state survive? And the key to that is being in a regime where one has sufficiently strong atom-photon interactions that gives you a way to essentially have information sort of exchanged between the two atoms without leaking out from the system. So there's a figure of merit for that, which is how strong is the atom-photon interaction compared to decay rates in the system, like the atom spontaneously emitting and the photon leaving the system that way, or the photon leaving the cavity mirror. If I want to do an entangling gate between two atoms, there's a number called the single atom cooperativity, which is that ratio of interaction to decay rates, which should be large. That is larger than 1 in our system, but more importantly, if I want to generate entanglement in this sort of more massively parallel fashion with many atoms, it suffices actually to have what's called a large collective cooperativity. The atoms, different atoms, sort of their scattering constructively interferes and gives me an enhancement in the interactions. And that's also something that we benefit from in being able to make entangled states of these ensembles.
Okay, yes, and again, please use your mic.
Again, thank you very much for a wonderful, wonderful lecture. Really enjoyed it. You gave a very good explanation for how you create an entanglement between a pair of atoms, let's say Alice and Bob. But then you showed us a picture of a bunch of atoms where every two are entangled. But once Alice is entangled with Bob, by the procedure that you explained, if Alice now gets entangled with somebody else, she loses the entanglement with Bob.
Yeah, so there's actually a property called sort of monogamy of entanglement, right? I can't have Alice and Bob maximally entangled and also Bob and Charlie, right? So it turns out there's sort of a whole zoo of different types of entangled states, and some of them involve sort of maximal entanglement between pairs of atoms. But what we have is something where it's sort of weaker entanglement between all of the atoms. So if in the simplest case where all of them interact, any given pair becomes weakly entangled, and no single pair is actually in this maximally entangled state.
Okay, thank you.
Mm-hmm. And in some sense, that can be sometimes more robust, also to sort of related to the previous question.
Okay, other questions? Well, if not, can I ask a question quickly? You spoke at an earlier point in your talk about optimization. And to optimize in the way you describe it, I have to get energy out of the system. So how do you do that? Because most of the mindset here is unitary propagation, time evolution, which conserves energy. So to do optimization, how do you get energy out so it finds the minimum?
Yeah, so let me say a few things about that. So first, one thing that we can do is to start in the ground state of a particular system. So for example, in this three-level system, if I start with the 0 state being the lowest energy state and put all atoms there, then we do start in the ground state. Somewhat surprisingly, and yeah, this actually surprised me initially, if we just do the simplest thing of suddenly turning on interactions and measuring correlations, the states that we see, you would think, why should that give me anything like a low temperature state? But the states that you initially get look a little bit like a low temperature state of a classical XY model, and that's because we can exchange interaction energy for the internal state energy initially goes up and the interaction energy goes down. But that's probably not a good way to actually solve the hard problems. And now, so now you could imagine saying I want to do some very slow quench where I change the parameters of my Hamiltonian and adiabatically stay in the ground state. And that's one approach that we're interested in exploring, but there's subtleties. If you try to go really slow, the fact that there's some dissipation in the system will matter. Another thing you could ask is there some sort of optimal control that will help you sort of steer a path that keeps you, that lands you in the ground state? But it's not, and then there's a question of could you use dissipation, right? So there's some light leaking from the mirrors. Is there a way to use that to your advantage? I don't know the answer to the question, but these are all things that we think we have a sort of nice platform now for being able to explore.
Great.